Hello and welcome back. In this video, we'll be working through a few examples of graphing functions of two variables. So we're going to work through three examples: this function, and lastly, this function. Now what this is going to come down to really is recognizing quadric surfaces. So I'll give you a little rundown on how we can do that if you don't have the best memory, and I don't, and so I'll show you the technique I use to recognize these quadric surfaces. So we'll start with this function. Here I have f of xy equals 2x plus 3y minus 12. So this is a polynomial of two variables, and really it's a linear function of two variables, right? We just have 2x and 3y, and then this constant minus 12. So what we do for this is we set the output of our function equal to our z variable. So here's my z-axis, my y-axis, and my x-axis as we normally have it. And I'll set z equal to f of xy. And that'll give me z equals 2x plus 3y minus 12. And the standard technique here is to try and recognize, so play around with this, massage the equation a little bit, and try and get a standard form of a quadric surface. So here, before I do any of that, because we have to sort of know what form to get it into, I can recognize that, right, we just have a constant, or a coefficient on the x, a coefficient on the y, and a coefficient on the z. So what this looks to me is a plane. In order to get it in the form of a plane, I need all my variables on one side and the constant term on the other side. That'll help me identify the normal vector to the plane, and that'll allow me to graph it. And so that's my next move here, is I'm going to move all these variables. I have a couple choices here. I'm going to subtract my z over and add the 12. So I'm going to get 2x plus 3y minus z equal to 12. And this is now in the standard form of a plane. So I can recognize this is a plane. My normal vector for my plane, right, that tells me the direction of the plane is 2, 3, negative 1. Now that doesn't actually help me to graph this so much. What I really need to graph this, or what can help me with a plane to graph this, is to understand the intercepts. So the y-axis, the y-intercept, the x-intercept, and the z-intercept. So in order to get those, I'm going to set variables equal to 0. So if I want, let's see this. So if I want the x-intercept, if I want the x-intercept, that's when y is equal to 0 and z is equal to 0. So for the x-intercept, I set y equal to 0 and z equal to 0. Now this should kind of remind you of graphing just a line, right? We can graph a line really easily by finding the x-intercept and the y-intercept and then connecting them up with a line. But in 3 dimensions, functions of two variables, we're going to get all 3 intercepts and then draw a plane through those 3 points. So the x-intercept, set y equal to 0, set z equal to 0. So what does that give me? That's 3 times 0 minus 0. I get 2x. So this tells me then that 2x is equal to 12. That gives me x is equal to 6. And so my x-intercept is the point 6, 0, 0. So I'm going to go ahead and mark that on my axes. Maybe I should draw some tick marks here. Let's do 1, 2, 3, 4, 5, 6. I really just want a rough sketch. I don't need to make this exact. So I'll go ahead and mark 6, 0, 0. Let's do a y-intercept. So that'll be when x is equal to 0 and z is equal to 0, right? The y-axis has coordinates that look like 0, y, 0. And that will give me 3y equals 12 when I go to my equation. And so that gives me y equal 4. And so that gives me the point 0, 4, 0. And I'll go ahead and mark that point. So that's right here. Lastly, I'll do my z-intercept. So let me maybe put that up here, z-intercept. I should move this up a little bit. Some of it's out of the frame. I apologize. Z-intercept. So the z-intercept, I get from setting x equal to 0 and y equal to 0. And that will give me, so looking at my equation here, then that'll give me minus z equals 12. Right, so that gives me z equal to negative 12. So my z-intercept is 0, 0, minus 12. And so that's, oh boy, maybe I should go by 2's here. I'm just going to do that. 4, 6, 8, 10, 12. And there will be my z-intercept. And now I have the plane that contains those 3 points. It's a little bit difficult to sketch a plane like this, but having our intercepts certainly helps. And then using technology will help as well to visualize this thing. So I'm going to go ahead and jump to a visualization of this plane. So if you're using GeoGebra, you could just put in either the function or you could put in the equation and it'll generate the plane. I'm going to use an interactive figure here and just show you what the final result is. So there's my intercepts, and then we draw a plane through those 3 points. Remember that 3 points, is so long as they're not collinear, not all on a straight line, will generate a plane, and here is that plane with the intercepts that we found. And so that is the graph of this function. Pretty cool, right? All right, let's take a look at another example. So here we have the function g of xy equals x squared plus y squared. Let me jump back. I forgot to talk about domain of this thing. I mentioned this was a polynomial in terms of x and y, and so our domain, and especially if we look at the graph, the plane that comes out, which is the graph of our function, if I pick any point in the xy plane, it'll have some corresponding point on the graph of the function. And so the domain is all x and y. And you can also see that in the algebra. There's no sort of combinations of x and y I can put in to really mess this up and to get outside of the domain. So the domain for this one was all xy in R2. Actually, I'm just going to say the xy plane. Domain, the xy plane. All right. Well, here we have another polynomial of 2 variables, right? I have x squared and y squared and coefficients on those. So this is another polynomial in 2 variables. And so again, my domain is all of the xy plane. So the xy plane is my domain. Here's my x, here's my y, here's my z. So no matter what point on the plane, I should be able to either go up or down and hit a point on the surface. All right, so we'll proceed in the same way we did last time. Our first step is just setting z equal to g of xy, the output of the function. So we'll have z equals x squared plus y squared. And now we need to ask ourselves, does this look in any way like the equation for a quadric surface? And this is really the tricky part with these sorts of problems, is we have to be able to recognize those standard forms for our quadric surfaces. And my memory's not so great. I don't have the best short-term memory, so I can't always, off the top of my head, remember the forms for all the quadric surfaces to be able to recognize that. And so one thing I can do is jump to the textbook. So here I am just in, this is section 13.6 where we first talked about quadric surfaces. And this is a really good place to come to when you're doing problems like this, right? Because in this section we have a table of all the quadric surfaces and the forms for their equations, the standard equations for these. And so let's see, what am I trying to recognize again? I had z equal x squared plus y squared, and I have to ask myself, I have to go through these and see, are there any selections of a, b, and c that will give me z equal x squared plus y squared. And so I can kind of scan through these and see, oh, in this case, that's the elliptic paraboloid. I have z equal x squared, so my a would be 1, and my b would be 1. And remember, that is that generates the elliptical traces. So the fact that A and B are both 1 means I'm going to have circular traces, and this is really going to be a circular paraboloid. So let's go ahead and graph this thing. I now know what it looks like. It's going to be an elliptic paraboloid, and I can graph it. Let's get a good sketch. So this gives me an elliptic paraboloid. And maybe I'll just make a comment that A is equal to 1 and B is equal to 1. So for instance, if I do a trace at z equal 1, I'll get 1 equal x squared plus y squared. And that's a circle of radius 1. So that's a pretty important one to do. Maybe I'll mark 1 here, and then I'll have, let's do 1, 1, 1, 1. This one's negative. And so I can now, I should be able to now draw a circle of radius 1 at z equals 1. There it is. I have my point at the origin, right? 0, 0, 0 is a point on this thing. And I know I have parabolas in the other directions. Parabolic. This one's coming towards me. On the other side. And so here's my elliptic paraboloid. Again, any point in the xy plane, even if I'm way out here, I'll be able to take a line parallel to the z-axis and go up, and eventually I'm going to hit this surface, right? Because these are parabolas. There's no asymptote here. These go on infinitely in the x direction and the z direction. So eventually I'll hit any line exactly once. So that one's not so bad. We just had to recognize this was an elliptic paraboloid and remember how to graph those. Last one, we'll take a look at this function, h of xy equals square root of 1 plus x squared plus y squared. I'll start, maybe start by thinking about domain because this is no longer a polynomial. I'll think of domain. Remember, I need everything inside of the square root has to be greater than or equal to 0. So let's say domain here. We need 1 plus x squared plus y squared to be greater than or equal to 0. And so we could mess with this a little bit, but we could also just recognize x squared is greater than or equal to 0, y squared is greater than or equal to 0 because it's the square of a real number, and then 1 is strictly greater than 0. And so this is always strictly greater than 0 and certainly greater than or equal to 0. And so any values of x and y will work. And again, our domain is all of the xy plane. Now let's try and graph this thing. So again, I'm going to start by setting z equal to the output of my function, 1 plus x squared plus y squared. And I can ask myself, yeah, does this look like any of the quadric surfaces? Oops, wrong scene. Does this look like any of these quadric surfaces? Let me try and make this a little bit bigger in case you're having a tough time seeing it. Does this look like any of the quadric surfaces? Notice none of the quadric surfaces have a square root in them, right? So maybe before we do that, let's jump back and let's square both sides. Keep in mind, z is always positive here. So I'll make a little note of myself. Note that z is greater than or equal to 0 for all x and y. For all pairs x and y. And so z squared is then equal to 1 plus x squared plus y squared. Let's see, I can now ask myself, does this look like a quadric surface? Let's jump back to that scene. Do any of these look like that? Remember, it was z squared equals 1 plus x squared plus y squared. So I have z squareds and I have x squareds and a y squareds, and I have a constant term, so that's what I'm looking for here. Ooh, this looks good, right? I have a constant term, I have x squareds, y squareds, and z squareds, and so this fits. Also a hyperboloid of one sheet fits. So it's got to be one of those two, and it really is going to come down to what are the signs on my x's and y, my x squared and y squared, when I sort of put all these variables on one side. So let's go ahead and do that and see what we come out with. So I'm going to bring all my x, y's, and z's to one side. I'm going to get minus x squared minus y squared plus z squared is equal to 1. And that fits exactly the hyperboloid of two sheets that we had on the last screen. Oops. So this is a hyperboloid of two sheets. Actually, do you see a problem with that? It's not quite a hyperboloid of two sheets, but rather, because z is greater than or equal to 0, if we jump back to the hyperboloid of two sheets, remember that there are two sheets to that hyperboloid, right? There's an upper sheet and a lower sheet. This is not, as we talked about in the last video, is not the graph of a function of two variables, right? And so this output, I have z greater than or equal to 0, and so what that means is I have just the upper half of this hyperboloid of two sheets. All right, there we go. So this is not a hyperboloid of two sheets, but rather the upper half, or the upper sheet of a hyperboloid of two sheets. And I think rather than graph this here, I mean, we could take some time and actually produce a graph and draw that hyperboloid of two sheets. I can recognize here I have A equal to 1, equal to B, equal to C. They're all equal to 1. So that gives me some information. I could then sketch this hyperboloid of two sheets if I needed to, or I could just use technology and draw it. Again, if you're using GeoGebra, you could either put in the function. If you put in this equation, right, if you just put in this equation, it'll give you both sheets, and so you just have to remember we're just looking at the upper half. Okay, that's it for this video. Hopefully I've given you a good strategy for identifying these things. Don't be scared to go back in your textbook to something we've already learned. The tables in this book are really good and really helpful, especially that table of quadric surfaces from section 13.6. So don't be afraid to jump back to that. It's what I do. All right, I'll see you in the next video.